Yo, what's up everyone? It's Operations Research Bit, and we're back again with another deep dive into the world of AI. Today we're talking about large language models, the brains behind everything from chatbots to content creation. You've probably heard of ChatGPT or maybe even BARD, but have you ever wondered what makes them tick? We're talking about the underlying architecture of these models, the blueprints, the framework, the stuff that makes them go. We're going to break down the 6 core LLM architectures that are dominating the AI landscape in 2025. Get ready to explore the differences between encoder-only and decoder-only models, dive into the world of encoder, decoder, and mixture of experts, and even wrap our heads around state-space models and hybrid architectures. Trust me, by the end of this video, you'll be fluent in LLM architecture, and you'll know exactly which model is right for the job. Whether it's generating creative text, translating languages, or even powering the next generation of AI assistants. Let's get started. First up, we have the encoder-only architecture, sometimes called autoencoders. Imagine feeding a whole sentence into a machine and it not only understands each word but also the context and relationships between them. That's what encoder-only models are doing. They use something called a bidirectional transformer encoder, which basically means they're analyzing the text from both directions, left to right and right to left, simultaneously. Now, how do you train a model like this? Think of it like a word game. We hide certain words in a sentence, and the model has to guess the missing words based on the surrounding context. This is called masked language modeling, or MLM, and it's how encoder-only models learn to understand language so deeply. And because of this deep understanding, they're incredibly good at tasks like text classification, sentiment analysis, figuring out if a piece of text is positive or negative, and even creating embeddings, which are like numerical representations of words that capture their meaning. Some prime examples of encoder-only models out in the wild are BERT and RoBERTa. These are the heavy hitters of text understanding, and they've really changed the game in natural language processing. Next up, we have decoder-only architectures, also known as auto-regressive models. If encoder-only models are masters of understanding, decoder-only models are the creative geniuses of the LLM world. They're all about predicting what comes next in a sequence, like predicting the next word in a sentence. Think of it like this. You give the model a prompt like, "the cat sat on the," and it has to figure out the most likely next word, which in this case is probably "mat." This prediction process is called causal language modeling, or CLM, and it's the foundation of how decoder-only models are trained. And because they excel at predicting what comes next, decoder-only models are the go-to for tasks like text generation, writing stories, poems, even code. They're also incredibly good at few-shot prompting, which means you can give them just a few examples, and they can adapt and generate similar content. Some big names in the decoder-only world are GPT-4, the latest and greatest from OpenAI, Llama 3, and Claude, known for its safety and less biased outputs. These models are pushing the boundaries of what's possible with AI-generated text. Now let's talk about encoder-decoder architectures, the bridge builders of the LLM world. These models, as the name suggests, combine both an encoder and a decoder. The encoder takes in the input, processes it, understands it, and then passes that understanding onto the decoder, which then generates the output. Think of it like translating between languages. The encoder takes in the source language, like English, understands the meaning, and then the decoder generates the equivalent meaning in the target language, like Spanish. This process is often trained using something called sequence-to-sequence objectives, where the model learns to map one sequence of words to another. But encoder-decoder models aren't just good at translation, they're also really good at summarization, taking a long piece of text and condensing it down to the key points. And they're great for other input-output tasks like question answering and even chatbot interactions. Some well-known encoder-decoder models include T5, which stands for Text-to-Text Transfer Transformer, and BART, which stands for Bidirectional and Auto-Regressive Transformers. These models are incredibly versatile and powerful tools for a wide range of NLP tasks. Alright, now we're getting into some seriously advanced LLM territory with mixture of experts, or MOE, architectures. These models are all about efficiency and scale. Imagine having a team of specialized experts, each with their own unique skills and knowledge. When you encounter a problem, you wouldn't ask everyone on the team to solve it, right? You go to the expert who's best suited for that particular problem. That's the basic idea behind MOE. Instead of activating all parts of the model for every single input, MOE models have these expert submodels, and a gating network decides which experts are most relevant for a given task. This means only a small portion of the model is activated at any given time, making it much more efficient and allowing us to build absolutely massive models with billions, even trillions of parameters. And because they're so efficient, MOE models are great for handling complex tasks with massive datasets. They're also really good at personalization, as different experts can be trained on different types of data, leading to more tailored outputs. Some key players in the MOE space are DeepSeek V2, known for its massive scale and ability to access and process information from the real world, and Llama 4, which takes the already impressive Llama model and adds in the efficiency and power of MOE. These are some of the most powerful and exciting LLMs on the planet right now. Let's switch gears a bit and talk about state space models, or SSMs. These models are kind of like the new kids on the block, but they're already making waves in the LLM world. One of the challenges with traditional transformer-based models is that they process information token by token, which can be computationally expensive and inefficient for really long sequences of text. SSMs offer a different approach. Instead of relying on attention mechanisms, they use something called state-based transitions. Think of it like tracking the state of a system over time. As the model processes each word, it updates its internal state, which represents the information it has gathered so far. This state-based approach offers several advantages. First, it's computationally more efficient, especially for long documents, because it doesn't have to process the entire sequence every time. Second, it can lead to faster inference times, meaning the model can generate responses more quickly. And third, it can be more memory efficient, which is really important when you're dealing with massive models and datasets. One example of a cutting-edge SSM is Mamba. It's still early days for SSMs, but they have the potential to revolutionize how we process language. Last but not least, we have hybrid architectures. This is where things get really interesting because it's all about combining the strengths of different architectures. Think of it like building the ultimate LLM, taking the best features from each approach and putting them together. For example, you could have a hybrid model that uses a transformer-based encoder for its powerful text understanding capabilities, and then combines it with a state-space model decoder for its efficiency and speed in generating responses. Or you could have a model that uses MOE for certain tasks and a more traditional transformer architecture for others. The possibilities are really endless, and that's what makes hybrid architectures so exciting. They allow us to be flexible and tailor the model to specific tasks and requirements. One example of a hybrid model is Jamba, which combines the strengths of transformers and SSMs. So, there you have it, a breakdown of the 6 core LLM architectures shaping the world of AI in 2025. From the text understanding power of encoder-only models to the creative prowess of decoder-only models, the versatility of encoder-decoder architectures, the scalability of mixture of experts, the efficiency of state-space models, and the boundless possibilities of hybrid architectures, it's an exciting time to be following the world of LLMs. Each architecture has its own strengths and weaknesses, making them suitable for different tasks. Understanding these differences is crucial for choosing the right model for a given task. Whether you're building a chatbot, generating creative text, translating languages, or powering the next generation of AI-powered applications. Thanks for watching, and don't forget to like and subscribe for more tech insights. As always, thanks for watching. Don't forget to like, subscribe, and hit that notification bell so you don't miss out on our future deep dives into the world of AI and emerging technology. Until next time.